This is a dramatic reading of Sexy's Standard Model Symmetries 2, Experimental Corrections, a blog by the Standard Physicist, available at science20.com. Now, thanks to all those folks who saw my previous blog, Sexy's Standard Model Symmetries, most of you probably did not follow the technical discussion that went on between David Halliday and myself at science20.com. I was pretty darn sure that I had a way of representing electroweak symmetry using quaternions. And David was pretty darn sure I did not. Such exchanges can go on for quite some time unless one party finally sees that they were in fact wrong with the facts. And that does not happen very often. It did happen here, and I was the one who was wrong. This blog, video blog as it were, goes into my mistakes and actually generates a few animations which might actually shed some kind of explain why I made the mistake I did. And because of that, I don't feel so bad. It's okay in science to be wrong sometimes. It's not okay to realize you're wrong and then not admit it. That's a problem. Okay, so I did not actually ever have a class on group theory. I don't say that with the usual classic fringe physicist false, pride bluff about, although I did not study this particular subject, I do know, well, they are very, very wrong, and I am brilliant. No, not. Instead, I actually get in a much more defensive posture, because I really want to hold on to whatever accurate definitions they give me, and then adjust as necessary. It's much more of a dodgeball mentality when playing against the more experienced kids. I mean, I'm going to get hit a few times, but I'll survive, and if I'm lucky, I might catch one of those things flying by, and I think that will help me grow and mature and play a better game of science. So let me review the basics of group theory that I know. All right. And number one is that there is a set of members of the group. The group has a binary operation. Call it multiplication, or you can also work with addition, but just don't use both at once. A group has an identity element. It's usually going to be 1 for multiplication or 0 for addition. And it has the property that when you take a member and do that multiplication or addition thing, that binary operation, you get back what you started with. You get back the same member. And the key one is that one member of the group times another member gives you a third member of the same exact group. All right? And every member has an inverse. So when working with group theory, just stick to one operation, and that's what I'm going to do here. It's going to just be 100% multiplication. A representation of a group defines what the math widget is one is working with, along with that rule for multiplication, that binary operation. Now, it can be all kinds of things. I mean, mathematicians are creative sorts. But I'm going to work exclusively with quaternions over the field of real numbers using the standard quaternion rule for multiplication. Now, one unusual way I approach these issues is by generating animations. One must be careful not to be misled by these pictures. That has happened to me. The animations must be consistent with all that is already known about groups, which is an awful lot of stuff. Now, a reason I actually do this, from a biologist kind of perspective, is because visualizations use different sections and, in fact, larger parts of the brain. Now, I have demonstrated some sloppiness with mathematical physics language, but I am making a good faith effort to speak more precisely. Now, most of folks actually avoid, most professional folks, I should say, avoid making images of what they're working on that have the same faithful content as their algebra. And it's actually a dream of mine that this will actually become a practice in the future. Enough of this pre-ramble kind of thing. On to the unitary group U1, which is considered quite simple. It is a unit circle in a complex plane. Now, parameterize this group with the norm of a quaternion, and oh yeah, make sure that really it doesn't have that much variation going on. All right, so so what I did for this thing was I grabbed a specific quaternion. I grabbed 1, 2, 0, 0. Okay, and I multiplied itself like 300 times. That was enough to make it look nice and continuous. And you get this perfect circle in the right-left plus time complex plane. Time marches forward in the up-down plus time and near-far plus time complex planes. The animation creates a straight line in space. The highest speeds happen at the creation and annihilation events, and the slowest speeds happen at the turnaround point. I also spent some time thinking about this parameterization. You see with that exponential in there? I mean, it looks like it destroys the scalar part of a quaternion. And when I multiplied this thing out, 300 times by other members of it, the animation looked identical. And that has now become a core method to this approach. If it looks identical in the animation, then it is identical. I mean, well, not a complicated concept, but and so the 3 complex planes were the same, and the animation was the same. The case is closed as well. And in fact, the algebra is kind of simple. There exists an imaginary number C. Let's go get it like so. There we go. That that will equal A plus B. So so the real deep take-home message of this napkin is that how a group is parameterized with a quaternion representation doesn't matter. And that's what David tried to say in quite a few different ways. The pictures agree. David was right, and I was wrong. All right. So I decided to stick with the normalization parameterization. Not that it matters, okay? And I actually wrote some tools to play with that parameterization. One was to vary, if I had a quaternion A, B, C, D, I wrote a tool to vary just A, or B, or C, or D, or AB, or AC, or AD, or BC, or BD, or CD, or ABC, or ABD, or BD, C, D, or A, B, C, D. Because when I do an experiment, I use a shotgun. And when I use this in this particular case here, I varied just the A part of the U1, and it looks exactly the same as just varying the B part, and that looks just the same as varying A and B, And so the observation I found of interest was that, I used just one complex number to fill up that animation by using its powers. And then I said, no, let's not do that. Let's just fix the imaginary number and vary the real number, and visually they are the same. Or fix the real and vary the imaginary part, and it's totally the same looking thing. All right? Now, what I did was I took that observation into trying to study SU2. And I worked with this quaternion 1, 2, 3, 4. And I normalized it, and I multiplied that 300 times, and I got this animation. But you look at this and you go, man, that looks a lot like U1, only it's tilted. Is that enough? Well, I thought it was, maybe. And then I thought about it some more, and it's actually easy enough to come with a one parameter way of writing the group, and we'll just show it right here. That thing, and then all you have to do is vary that 1A, and you should be fine. So this animation is not a way to represent the group SU2. But didn't I say in Sexy Standard Model Symmetries video blog that was a way to represent the group SU2? Yes, it was. Oh, so I was wrong. Okay. And I've actually thought that way for quite some time. But I am wrong. I wish I was always right, but I'm not. So it was really this property of the group U1 as a quaternion that misguided me. And I feel less bad now that I understand why I went down that wrong path. So now let's see if we can get to the right animation of SU2. Let's first, though, consider what R4 really looks like. And here's an animation where I try to fill up a cube of spacetime. Now, some are going to complain that this blinks a little. I try to avoid that by using 100,000 quaternions, and then 300,000 quaternions, and then 1,000,000. And what you're actually seeing here is 1.5 million quaternions trying to fill up 8 seconds of space-time, and it's not giving a steady picture. This is kind of fun for me because the image has demanded more resources than my hardware was kind of willing to deal with, and in order to just fill up space-time and give me a full dull wall. It didn't pan out. I don't know if I go to 10 million. 50 million do I have to go before I can make a solid block? That's kind of interesting. So I can, though, take my normalized quaternion and vary all 4 numbers that go into the normalization. And this is the animation of SU2. This is consistent with what people expect to see of the group SU2, the surface of this expanding and contracting sphere. The sphere starts out at the point -1, 0, 0, 0. It reaches a maximum radius at time equals 0, touching the extremes of ±1 at up, down, near, far, right, left complex planes. One member of this group times any other member will end up at a third member. all three probably in different frames of this animation. The multiplication will not commute because we are covering all the angles in space-time with this one. And, you know, some 600,000 quaternions were used in this animation. And here's another detail I find of interest. I plucked actually only 2,000 random values for A, B, C, D. And then for each of those, I took 400 products of those because I found that, 300 products of those because I found that 300 would make a smooth representation of U1. And so that means that much of what you're seeing in this SU2 animation is really getting filled up by using U1 subgroups. What does it look like if only 3 numbers are varied instead of 4? Well, I wasn't sure. For that one that I wasn't varying, I mean, should I put it to 0? Or should I give it a value, like 0.5? And when unsure, a shotgun man decides to do both. So this first one, I have the zeros in there, and you get, you can see, hey, that guy stays like 0. And this other one, well, neither of these animations are groups. I mean, values are missing, and, if I take 2 values within this, I should be able to get to that kind of place that's like missing stuff. I'm actually not completely convinced that that is the case for the ones that I didn't put a 0 in. It's something I'm kind of investigating as I go on. But here's kind of the deep take-home message, as it were. What I had wanted was an animation of electroweak symmetry, U1 cross SU2. But what I got was really SU2 with as many U1 groups packed inside there as I chose to calculate. And that actually sounds more subtle than lifting something from Professor Glashow, who won a Nobel Prize for electroweak symmetry. So I'm going to take door number 2. That would be SU2 with a whole bunch of U1s packed inside. Alright, so here's my snarky puzzle. Be a flatlander. Imagine what it looks like if you only varied 2 numbers for that non-zero constant animation. Wear a bow tie to celebrate your correct answer. Thank you very much.